Now I'm pleased to introduce my good friend and esteemed colleague, Dr. Daryl Greenfield, Professor of Psychology and Pediatrics at the University of Miami. His presentation is called Making Science and Engineering Visible in Early Childhood, and it will be followed by a live Q&A.
Dr. Daryl Greenfield, Professor of Psychology and Pediatrics at the University of Miami, now presents Making Science and Engineering Visible in Early Childhood.
Good afternoon. I'm Daryl Greenfield from University of Miami, and I'm going to talk to you this afternoon about making science and engineering visible in early childhood. There is considerable reason for why STEM and science should be available and something that is important for early childhood. There is both theory and research and movements both at the local and the state and the national level to increase STEM in early childhood. Here is a quote from a White House summit that occurred in 2016 under the Obama administration, trying to increase STEM in early childhood, and part of the information that was sent out indicated that research indicates that as early as infancy, young children start developing and testing hypotheses for how the world around them works. They understand probability and make predictions. They take in information from trusted sources around them and use that information to guide their behavior. And that all begins in the first year of life. As they progress through the preschool years, their curiosity continues to grow, and the sophistication of their reasoning and inquiry skills grow along with it. A year or so after the White House Summit, a report was published by a group of us entitled Early STEM Matters. Here is the link to the report. If you just click on this particular URL at the bottom of this page, you'll get access to the report. There's an executive summary sitting on the website, and there's also the ability to download the entire report, as well as learn who were the committee members that wrote this particular report. The report starts out with 4 guiding principles. And what is important about these 4 guiding principles is that 2 of the guiding principles focus on the critical role that adults play in the natural STEM learning inclinations of young children. So the first guiding principle says children need adults to develop their natural STEM inclinations. So although children are naturally interested in the world around them and interested in understanding how their world works, they need adults to help them with this natural inclination. If you look at the third guiding principle, it says that adults' beliefs and attitudes about STEM affect children's beliefs and attitudes about STEM. So the issue here is that we want adults not only to support children's natural STEM inclinations, but also do it in a positive way. And part of our report focuses on messaging with the notion that currently sort of the average adult, if you ask them about STEM and the importance of STEM in early childhood, will tell you that it's too early to do STEM with young children. STEM is too difficult, and if you expose children to things that you want them to learn that are too hard and too difficult, they will be turned off by learning, and they won't be able to learn this area, and then they won't want to learn it in the future. And then there's also sort of the attitude and belief that not everybody can do STEM, that it's hard for some people, and that you need aptitude, and generally the notion is that it's for boys and for older boys. But it turns out that this is clearly not the case, and that STEM actually is a critical time for early childhood is a critical time for exposing young children to STEM, which they naturally are curious and interested in, and we want adults to support this. So how do we make science more visible to the adults, all the adults in young children's lives? I want you to watch this video about sort of how to make things visible, including making science visible.
This is an awareness test. How many passes does the team in white make? The the answer is 13. But did you see the moonwalking pair?
So as this video says, it's easy to miss things that we're not looking for. So how do we make science more visible in early childhood? So what we have done is we have taken a framework that was developed starting around 2005, and it was actually published in 2012 by the National Research Council. It was a framework for K-12 science education. And what this new framework did was to try to get the K-12 system to change how science was fundamentally being taught. The review of the prior way science was taught in the K-12 system was that it was taught in a very fragmented, disconnected way, unrelated to students' lives. So students could do science, learn to memorize facts, spend 7, 8, 9 weeks on a particular topic, learn to read a particular word problem and figure out what information in that word problem you could stick into an equation to come out with the correct answer. And bright children and students can do this, but they would say, like, well, this is really boring. Why would anyone want to do this? And why would you want to have a full-time job doing this? So the new K-12 framework says what we want to do instead is we want to get children to learn by actively engaging in the learning. So there's 3 components to the new framework. They're interwoven so that they should be occurring at the same time. And the first question is, like, what are children interested in? The idea is to focus on interest, because we know that we learn better when there's something that's of interest to us to learn. So if we're goal-directed and motivated to learn in an engaging and interactive way on a topic that's of interest to us, we're much more likely to learn that. So what are children interested in? It turns out these disciplinary core ideas, a small set of ideas in science, life science, physical science, engineering and technology, and earth and space science, a small set of these core ideas are now what is the focus of this K-12 framework. These ideas should be learned by engaging children in practices. These are the behaviors that children engage in to explore and develop knowledge. So what can children do to answer their questions? And then the third component are called cross-cutting concepts. What are children trying to understand? These are the big ideas that emerge and generalize across all the science contents, creating a much more coherent worldview for students so that knowledge becomes more connected. Let me briefly show you what these things are. So science practices, the behaviors that children engage in to explore and develop knowledge. So these are part of the K-12 system, but if you look at them closely, these are things that infant, toddlers, and children, preschool children, are quite capable of doing. Asking questions and defining problems, observing and describing, making predictions, planning and carrying out investigations. Clearly, as that first slide with the quote from the White House says, infants start out not doing this as sophisticated as than toddlers and preschoolers, but they do become more sophisticated at this as they grow and develop. And by using this same particular approach, by the time they enter kindergarten, they've already had experience engaging in the scientific practices. So get children to learn by doing. Cross-cutting concepts. What are these cross-cutting concepts? These are things like patterns. Patterns are everywhere. Cause and effect. Cause and effect relationships are everywhere. Systems and system models. The whole notion that components are put together and they work together. Even an early childhood preschool classroom is a system. Particular children get assigned particular roles, and if a particular child is missing on a particular day, either someone else needs to fill in, or that role ends up being not happening, and then the system is not working the way it should be. Structure and function is an important cross-cutting concept. So we can often tell what something does, what's its function, by looking at its structure. So for example, if you look at a spoon versus look at a fork, Why does a spoon not have holes and a fork does have holes? Why does a fork have prongs? And the answer is their structure is related to a slightly different function. Spoons are to hold liquids. A fork cannot hold liquids, but forks can stick a fork into something and pick it up that you probably can't do as easily with a spoon. So cross-cutting concepts involve thinking. So we want kids to be doing and thinking, and then we want them to do that around a series of disciplinary core ideas. So things that young children are interested in, that's physical science, for example, what things are made and how they move. In life sciences, the needs and characteristics of living things, earth and space science, the environment, the weather, how humans interact with the planet. And then for engineering and technology, how things are designed and used to answer questions and solve problems. One of the things that is really nice about science and STEM is that it doesn't have to be a pan curriculum that everyone does, whether it's relevant or not to their local context or their local culture, but instead what you can do is take advantage of what's occurring naturally in young children's context and their culture and generate the questions, what are children interested in based on what their direct experience are. So here's an example of one of our early childhood centers where you have plants growing on walls, and children wanted to know, how can plants grow on walls? We thought plants have to have roots in the ground. So this is a topic that children can explore, and it's relevant to them, and they're motivated to learn this topic because it's something that has a relevance to their local context. Patterns is one of the cross-cutting concepts, and what you can end up doing is on everyday activities, you can look for patterns. So for example, if you live in an urban city and children are crossing streets, which is an important safety sort of thing to learn early on, the lights at the crosswalks follow a pattern, right? They go green, yellow, red, and they do that continuously. So you can look for that pattern. And in terms of thinking about colors often on these street lights have meaning beyond just what the street light is. So if you see the color green, usually green means it's safe to go somewhere on a sign. Yellow means caution, and red usually means stop. When you're crossing a crosswalk, there's an area that you need to be in to make it safe to crosswalk. And the crosswalk, if you look at it, has a typical pattern to it. This particular pattern shows the borders of the crosswalk, so where do you have to stay between the two lines, and then you've got the horizontal lines that make the pattern that go across the entire crosswalk. Patterns occur in everybody's neighborhood. So if you live near a railroad station or a metro station, the tracks have a pattern. The bricks on a wall have a pattern. And what is interesting to notice is that when children, preschool age children, start to build structures, they typically do it in the block area by building one column of blocks, and then another column next to it, and a third column next to that, and then that typically falls over. Whereas if you look at the pattern on a brick wall, you see that the bricks overlap. And if children notice this and take a picture of this, then they try to build their own structure in that way, and they find out that structure is a more stable structure. And you can find patterns on buildings. You can also find patterns. This is a kitchen of one of the children's homes. You find patterns on the floor. So hunting for patterns, you can find them in the environment. This is a human-made environment, but also patterns happen in nature. So you can examine plants and plant leaves. You can take them into the classroom and use a magnifying glass, and you can see that patterns are there as well. So what I'm providing here is 2 links to videos that I helped create for an organization called 0 to 3. They are currently the Head Start National Center on Early Childhood Development, Teaching, and Learning, and I'm one of their advisors. And a couple of summers ago, we created these videos to give adults sort of a sense of what does this look like in everyday experiences. So the first video, Everyday Fun with Science, shows infants and toddlers and adults in everyday activities with adults, and the narration is from the lens of science, to some extent using the framework that we talked about. Here's a second video, Everyday Fun with Technology and Engineering. It does the same thing, but now it focuses on technology and engineering and shows infants, toddlers, and preschoolers are trying to solve problems in everyday life with adults around them, and how the adults can help and support children's natural curiosity and their natural interest in engaging in science and engineering. We are involved in doing this work in a number of centers across the country. We're part of a network called Educare. If you just type in Educare Our Schools, you'll see all the schools that are involved across the country in the Educare network. And we're doing this work to try to develop a better understanding of science and engineering in infants, toddlers, and preschool age children in these centers. If you want more information, you can email us at our email address. You can go to our website, schoolreadinesslab.org, learn and play, and see some of the activities that we do. We have Facebook page and a YouTube page and an Instagram page where we have weekly activities for adults to do at home or in classrooms with their children. And hopefully you will take a look at these. And then the Connect with SE, if you click on the Connect with SE, it will take you to a Qualtrics survey. You can fill out information and we can use that to help contact you. So I'm gonna end here, and looking forward to spending some time with you after you watch the video to answer any questions that you may have.